Hello everybody. First of all, I will derive the time-dependent Schrödinger equation. Last time we derived the time-independent Schrödinger equation. Let me write the time-dependent one. And I will start with a bit of a spoiler. It is the time-dependent one. The time dependence is in the wave function. The wave function can be written as this way. We separate the variables like that. For this part, we write like a given, this exponential form. If we take the derivative of this form, we get if you plug this equation into this one, the time dependent one, we will get let me write energy in form of this equation. If you plug this one into the time-independent equation, we will get it's not enough space. I hate this. Instead of writing this, I will write the separated one. Oh, no. Plus, and for the right hand side, we have this. But instead of this, we can write this one, which we calculated here. Since R and T are separated, they are not connected, we can write like this directly. Taking the derivative of this one and this one are the same thing because it does not depend on T. Laplacian is just this. Oh, and this course. Okay. And for this part, same applies. We get the time dependency in Schrödinger equation. It is a very easy calculation, so I will move on from this one. And for the second part, I will be explaining the Zeeman effect, which is basically which shows you how energy levels splitting due to an external field, which is the magnetic field in our case. First of all, I will give a very quick glimpse on the hydrogen atom and its quantum numbers. It will be a high school level, I guess. But first of all, let me write the Laplacian again. for the XYZ coordinates, but we are talking about hydrogen atom, so it is a spherical structure. So instead we will be using the spherical Laplacian, which has a really ugly formula. In spherical coordinates, I mean r, theta, and phi. And by using this Laplacian, we will operate on the wave function in the form. Again, we are separating the variables. Like this. And we will get three equations: radial, azimuthal, and polar equations, which I will not write because it's as ugly as this one. But from these three equations, we will actually arrive another three equations. The first one being this, the energy. It is for hydrogen because it is easier to write that way. We are talking about hydrogen anyway. The second one is the angular momentum, but orbital angular momentum, its magnitude. It will be written as this way. L being the azimuthal quantum number. And N is the principal quantum number. And the third one is for the z component of the orbital angular momentum, which is just the magnetic or quantum number multiplied by HR. I think most of you know L, ML, and N from high school. We are writing orbitals by those three quantum numbers. Why I explained this quantum numbers is because of actually just this one. Because it is associated with Zeeman effect. This one. The L is azimuthal quantum number, which is the indicator of the shape of the orbital. And ML is the magnetic quantum number. It decides what direction is orbital facing. I mean, for example, if you look at the p orbitals are like that. Px Py and Pz. Those three have different spatial orientations, as you can see. And Zeeman effect happens when external magnetic fields applied. But those orbitals have degenerate energy levels, like we express them as the same energy level. But if there is external magnetic field, instead of one energy line, we have three energy lines. It happens because there are three different orientations for the p orbital, for the 2p orbital. they have same energy, they have degenerate energy at first without a magnetic field. But due to magnetic field, the tendency of magnetic field to rotate those three orbitals, you will experience three different energy levels because let's say the magnetic field in this way, this will orient different than this and this. I mean, you need to do more work on some of them, three of them, than the exact of. Okay. It takes less time than I anticipated. Oh. Okay, now I will move on what Schrödinger explains in his second lecture. In his second lecture, he says that the displacements of the lines are quantitatively described by the new theorem. He just mentions like that for all this part. He just describes like that. But he moves on how to explain intensity relations between the non-vanishing lines. Linear polarization, and selection rules. Firstly, he describes some wave function like this. This is a wave function such that they are all orthogonal to each other and they are complete, so that you can write any wave function as a linear combinations of those eigenfunctions, those psi k's. And I will write it like that for now. Those wave functions, as I said earlier, are orthogonal, which you can obtain this. They will give you 1. This one will give you 1. But since they're orthogonal, again, another wave function, which are not equal, k and l are not equal to each other, will give you 0. Since they're eigenfunctions, we propose that. Okay, let me first erase this one. In this formula, this frequency is associated with this wave function. But if you want to calculate a frequency which is not an VK's frequency, you need to look at this one. And he wants to make his wave function, he wants to attribute a physical meaning to his wave function. So he proposes this one. Let us think about this. And let us attribute the physical attribution, emission of light, for the wave function in this form. This is the charge density. And this is absolute electron charge. Okay. Here we write Vxt as this way. So let me write this one. We will get this configuration. Okay. If you integrate both sides, we will get this one. Because they are orthogonal, they will give 1 if they are equal. Then you get this one. And he says it should be equal to minus e. He does not elaborate any further, but he says that it does have to be equal to minus e. From there, we get this one. This one is actually the probability of finding, from that, the probability of this ck is the probability of finding vk in vx, and we get 1. The squares of these will give you 1, because it means that all the probabilities should be equal to 1. He derives it that way, and he proposes that he says that radiation of fluctuating density, rho, is nearly equal to electric dipole with electric moment. The z component of the electric moment is actually. And it has x and y components similar to that one. And he uses the rho formula. He uses this formula in here and gets another ugly formula. This AKK is this one. And he claims that this AKK is the amplitude of the dipole, corresponding dipole. Since he attributes this this description to this one, he further explains the intensity relations, near polarization, and selection rules with AKK as follows. selection rule is, I said that the p orbital has one energy level, and it has, with the magnetic field's influence, it has now 3 energy levels. But selection rule is when some of these 3 or maybe 5 or 7, I don't know, some of them may not be appropriate for some transition between some quantum state to another. You cannot have all these energy levels if you are transitioning from a quantum level to another. He explains this as when K prime disappears from all directions, from X, Y, Z directions. This is when the selection rule happens. And secondly, he attributes the intensity relations between non-vanishing states as Gauss K primes square. It is related with this. And he explains it like that because CK square has a physical meaning, it should have to as an intensity. Something like that. And lastly, linear polarization. It is when the electric or magnetic field in our case is constrained in an plane. And he explains it like that. AKKs are constants in XYZ directions. And let's say this one is 0, this one is 0, and there is only the Z direction. So linear polarization happens in that plane. Okay. Actually, it is all for this lecture. It is very short, I guess. How many minutes is that? Okay. Any comments, questions? Okay.
I want to why, like, as you said, Schrödinger said that this new theory explains the hydrogen line. Why the other previous theories cannot? Like,
what?
Have, like, why this new theory explains the hydrogen lines, but like we have previously that we have at master equation. We have a nice electromagnetic theory like sitting on.
Okay,
when
he
the
said
theory established, it was like on the view of, I guess, the electromagnetic theory, and why it doesn't explain what these theories can. Like, what is the problem?
there is no problem for the Siemens effect. Okay, he says that other old theories explain it, just like mine, the new theory. But what I am explaining, the intensity relations, linear polarization, etc., they do not explain it. The Schrödinger equation explains it.
Like, what is the problem?
What is the problem?
Why you cannot apply a electromagnetic theory on this electron one single division? Like, why you cannot solve the orbital division of the electromagnetic theory? Like, it's like two charges. You can easily find the stable positions around nucleus that has electron can be in, right? Like, because you have two charges. Why?
Okay, I think I don't know the old theories enough to answer this question. Do you have any explanation for that? Okay, then explain.
I want to.
No, explain.
Like, the main problem is that when you have an accelerating charge, it should be in maximum still there. Then consider just the electron orbiting around the proton. Like, you have a circular motion. Right? In circular motion, you always have an acceleration towards the center. That means that I want to say that, but it's in quote. So that tiny little electron should lose energy every time it rotates around the nucleus. So it should radiate and decay into the nucleus, and you get like neutral material. This is what I think.
So simply, we can't even construct a hydrogen atom in all theory.
Yeah,
So
like
how can we explain?
you cannot construct a stable hydrogen atom in all theory.
Okay, makes sense.
Where the electron rotates around the nucleus.
Okay, thank you for your explanation then. Any comments, questions? Okay.
What exactly was the AKK?
He says that it is the amplitude of the corresponding dipole. He just says that.
And do you have a relation between CK?
Okay. He says that. I mean, I don't get that part exactly, honestly. He says that it has a physical meaning. Then it should have a physical meaning, which is intensity. Something of those lines. I mean, I don't like his explanations in second part, honestly. They are not convincing enough for me.
Also, like he himself proposed that AKK is the polarization amplitude.
Mm-hmm. Dipole.
Dipole. But does he gives any reasoning why he thinks that way?
Before describing this, the problem is the fluctuating rho is nearly equal to an electric dipole. And from then on, he derives these formulas and says that AKK should be the amplitude of the corresponding dipole.
Because it's just multiplicative constant.
Yes.
I see.
Any other comments, questions?
I mean, it makes sense because CK is simply, not exactly, but simply the intensity of the wave function.
Yes.
And we obtained AKK prime from just writing the dipole moment corresponding to the wave function, K and K state, K prime state. So it makes sense actually.
Yeah, it makes sense, but not enough explanation for me. The second part, at least. Okay. Then we can end here if there's no any other question.